Welcome to the Problems channel season 2 episode 25, the episode which I titled Circle, Center, Straight Edge. Nope, because in this episode we will construct a proof that shows that it is impossible to locate the center of a given circle using nothing but the Euclidean straight edge alone. Before we do that, however, as a traditional and friendly reminder, if you are joining our channel mid-season, then first of all, thank you for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. I have framed the new challenge as the mathematical problem S2E25, and the objective of that problem is to show that given a circle without the location of its center, it is impossible to locate that center using the Euclidean straight edge alone. Here is a model of the Euclidean straight edge. This is basically a ruler that has no markings, and as a theoretical tool, obviously the Euclidean straight edge does not have any thickness, and sometimes the students of mathematics get quite wily and try to sneak in an infinite number of steps. So in a traditional geometric construction using the Euclidean tools such as the compass and the straight edge, here what we mean is the following. A geometric construction algorithm has a finite number of steps, and just to make sure and to lock things down, the description of that finite number of steps also must be finite. In that sense, in the mathematical problem S2E25, we are to show that given the Euclidean straight edge and a circle whose center is not known, the location of the center is not known, we're to show that it is impossible to locate that center using nothing but the straight edge alone. Now, as a small comment, back in my time, this type of problems would be formulated slightly differently. We will not be told right away that it is impossible, and the question would be framed as follows. What do you think? Is it possible or is it impossible to locate the center of a circle given nothing but the Euclidean straight edge? If you think that it is possible, then generate a finite description of a finite number of steps, following which, using nothing but the Euclidean straight edge, the unknown location of the center of a circle can be located and constructed. If you think that it is impossible, then generate a corresponding proof. Here, in some sense, I'm taking a little bit easier on our audience. I'm already telling you guys up front it is impossible, and the question is to generate a convincing proof. We will generate the proof of the impossibility to locate the center of a given circle using nothing but the Euclidean straight edge alone, using the so-called scope expansion problem-solving approach. And before we do that, I would like to take a few moments and explain how the scope expansion problem-solving approach works. According to the scope expansion problem-solving approach, if we want to solve this or that technical problem, then we may want to try to keep increasing or expanding the scope of the local material at hand, preserving the technical essence of the original problem until that original problem can be solved as shown over here. For those of our viewers who have studied the scope reduction problem-solving approach, remember that sometimes when we want to solve this or that technical problem, we represent that technical problem, let's say, with a box, and according to the scope reduction problem-solving approach, the idea is that sometimes the difficult to solve problem can be made progressively smaller, smaller, and smaller, and smaller in some sense until the original problem can be solved through the reverse process of expanding the smallest and simplest problem. And that is one way, or this is a way in which the scope reduction problem-solving approach works. Amazingly enough, sometimes in mathematics, theoretical physics, and computer science, it is possible to represent a given difficult to solve problem again as, let's say, a box, but instead of making that box smaller and smaller and smaller, as the scope reduction problem-solving approach prescribes. Sometimes it is possible to make that proverbial box slightly larger, larger, and larger as the scope expansion problem-solving approach prescribes. And in that process of expanding or making the box slightly larger, sometimes, amazingly enough, that process can shine a better light on the original problem at hand, and sometimes, or in certain cases, after we expand the local material at hand appropriately, preserving the technical essence of the original problem, we can make certain observations and then, in some sense, contract this larger box into the original box and thus solve the original problem. As usual, as with many problem-solving approaches, the newcomers to this whole idea are often befuddled or confused. What exactly does it mean to keep expanding or increasing the scope of the local material? Again, I think it's very difficult to give one concise, small, short, and very descriptive definition of what that means so that all the mathematicians in the room will agree on that definition. And as such, one of the best ways to study how this or that problem-solving approach works is to engage into a highly scientific doctrine of monkey see, monkey do. In other words, see how other people do that thing and then try to act by analogy and hopefully taking that idea further. For example, the phrase keep expanding or keep increasing the scope of the local material at hand may, for example, mean the following. If we work in a pronounced one-dimensional problem, maybe stepping out in a two-dimensional case may be helpful. If we're working with a pronounced two-dimensional case, maybe counterintuitively, maybe stepping from the two-dimensional space into three-dimensional space may help. Likewise, if we're working with a pronounced three-dimensional case, maybe sometimes stepping out into the four-dimensional space may be helpful, and so on. You get the idea. Also, sometimes in certain problems, and we'll see that in the near future, if we work with a polynomial, for example, of the first degree, this or that mathematical task may be accomplished if we amazingly and counterintuitively enough start working instead of first degree polynomials with the second degree polynomials and so on. For example, expanding the degree of the polynomial from the second degree to the third degree, from the third degree to the fourth degree, may provide us with a tactical advantage. In another case, if we're given, for example, a specific geometric shape that looks this specific way, maybe, as the scope expansion problem-solving approach prescribes, instead of looking at that shape as a whole, we may pretend or we may think that that shape is actually a smaller part of a bigger whole, and in a bigger setting, we may gain certain tactical advantages into seeing what is going on with the smaller part at hand. Also, likewise, for example, in real or integral calculus, if you will, it is possible to evaluate an integral when instead of dealing with one given integral, we introduce, for example, the second integral, and instead of dealing with one, we deal with two or maybe three integrals. Likewise, in the differential calculus, maybe in certain situations, instead of dealing with, for example, one equation, one differential equation of order 2, maybe we can split it into two differential equations of order 1, and it may be easier to deal with each such differential equation by itself, and thus that approach will allow us to solve the original problem at hand. And also, this is not a complete list, of course. There are way more scenarios. This is just some sampling. Sometimes when we are asked to prove, for example, a certain combinatorial identity, and proving these combinatorial identities is, on the one hand, a lot of fun. On the other hand, it could be quite challenging. But sometimes a proof of this or that combinatorial identity can be carried out precisely courtesy of the scope expansion problem-solving approach, when instead of working with one specifically crafted type of numbers, we expand the scope of that combinatorial identity and deal with a more generic case. And sometimes it may so happen that proving a more generic case, amazingly enough, is much more straightforward. And then we use the close cousin of the scope expansion. We apply the scope reduction and reduce the more general problem to a more specific problem. In this episode, trying to solve the mathematical problem S2M27, we will use precisely the scope expansion problem solving approach, and instead of staying within the confines of two dimensions, because a circle is usually thought of as a two-dimensional object, instead of staying strictly within the confines of the Euclidean plane or two space, we will step out actually into three space, and we will see how that works in a moment. Before we do that, I would like to show one perhaps silly example of how the scope expansion problem solving approach works. As such, here is one example that shows the mechanics of the scope expansion problem solving approach. This problem by now has become so popular that it's not really a problem. Just about everyone knows how to solve it. But on the one hand, that problem may seem to be silly. On the other hand, it's not really that silly for the following reasons. The objective of this silly problem is to take this 9 points arranged on a plane in a square formation, and without lifting the pen from the paper, cross all the points or cross all the dots in this arrangement in exactly 4 straight lines. Sometimes, especially the younger audience, when they try to solve this problem, they do not really see the solution, and this is exactly the point why this problem is not really that silly, because this problem shows that the psychology plays a very large role in technical problem solving, because whether consciously or unconsciously, the given problem, whatever it is, a problem in any vaguely defined layer of mathematics, a problem in any vaguely defined area of theoretical physics, or the problem in any vaguely defined area of computer science, that problem, whatever it is, becomes a box out of which many people simply cannot escape for various reasons. And probably here, that is how the psychology of solving problems enters the picture. Given this specific problem, over here, it may look like a box, but a literal box, but in general, when I say that a given problem becomes a box, it's not a literal box, but a proverbial box. And the inability to solve this or that technical problem means precisely that many people cannot escape or climb out of that box. Here, when we'll look at this arrangement of, or square arrangement of 9 points, whether we like it or not, consciously or unconsciously, again, for many people, this arrangement becomes the box, and that is how the problem possesses a challenge. And a lot of people do not really know how can it be done. How is it possible to connect all 9 dots with 4 straight lines without lifting the pen from paper? But if we use the scope expansion problem solving approach while attacking this specific problem, and we'll try to increase the scope of the local matter at hand, then we can solve this problem. And exactly how does that work? Well, instead of staying within the confines of the proverbial square that is delineated by these 9 points, we, at some point, let's say we start with the lower left point of this arrangement, we go up, but exactly here at this point, we expand the local material. In other words, we say that this box for us is not the box anymore. We step out of the box right here, and then we cross the points, this point and this point, diagonally with the second line. And here again, notice that at this particular stage of our solution of this problem, we step out of the proverbial box yet one more time, and we continue our line over here. So our solution so far looks as follows: 1, without lifting pen from the paper; 2, without lifting the pen from the paper; 3, and without lifting the pen from the paper; 4, and thus we visited all the points in this arrangement with specifically 4 straight lines without lifting the pen from paper. So this will be line number 1. Let's say we went this way. Here will be line number 2. We went this way. Here, this is our line number 3. we went this way, and this will be our line number 4, where we went that way. And once we unlock a solution of this problem, we understand that this problem can be solved in a number of different ways. This is not a unique solution. We can go, for example, in the opposite direction, 1, 2, 3, 4, with various twists and turns. And like I said, on the one hand, the problem may seem to be silly, that is given to kids. On the other hand, it's not really that silly. It shows that the psychology has plenty to do with technical problem solving, because this way or that way, consciously or unconsciously, a given problem, whatever it is, becomes a box out of which many people cannot step out. That's one hand. On the one hand. On the other hand, the reason that this problem is really not that silly is because we can, in some sense, inhale a little bit of real and grown-up mathematics into it, specifically the theory of graphs. If we represent, let's say, which one, the connection here, 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 and here, this will be our finite connected graph. And we remember that in the theory of graphs, the specific shape that connects the nodes of the graph, in other words, the given points, can be represented as the nodes of this graph, and our solution lines become the edges of this graph. The number of points, the number of vertices or nodes in this graph is finite. The number of edges is finite. This is a finite connected graph. We may say that it's not directed graph. And what exactly does this arrangement tell us? Well, remember that any isomorphic or continuous transformation of the given graph in such a way that any two adjacent points remain adjacent in the transformed version, then these graphs are the same. So here in this case, there exists an Eulerian path over this graph. There exists an Eulerian path. And what is the Eulerian path? The Eulerian path over a graph is a basically way to walk through the graph in such a way that each edge, but not necessarily each node of the graph, is visited precisely once. So this Eulerian path will go which way? It will start with A, then it will go B, C, D, E, F, G, A, and then H, and K again. Here's, for example, one path, right? Starting from the point A, B, C, D, E, F, G, A, back to A. We visit the vertex of this graph A twice, and then H, and then K. This is exactly one traversal of the a traversal of a graph where we walk over each edge precisely once, and we do that again without lifting our pen from the paper. And in some sense, this graph is isomorphic to this graph. And if we cleverly twist the edges over here and fold this graph into this one, voila, our solution emerges. Now that we more or less understand how the scope expansion problem solving approach works, we can take on the original problem, S2M27. The proofs of impossibility of doing something in mathematics are usually quite difficult to put together, and sometimes these proofs are quite drawn out, lengthy, and sometimes they're difficult to follow as well. And one of the reasons for that is because of the order that is placed on such proofs. That order is very tall, and again, the reason why that order is very tall is because such proofs have to eliminate all other possibilities. In other words, strictly speaking, in a finite number of sentences, we have to convince ourselves and the audience that no matter what else, no matter what other legal manipulations we perform in this or that scenario, the claim that is made in the statement of this or that theorem is still correct, and it is not possible to do this or that, no matter what. In our problem, however, that will not be the case, and amazingly enough, the proof that it is impossible to locate the center of a given circle with the straight edge, with the Euclidean straight edge alone in a finite number of steps will be way shorter than the length of all the supporting material, And the reason why that is the case is because we will be using precisely the scope expansion problem solving approach. That is, when most students are told that it is impossible to locate the center of a given circle with the Euclidean straight edge alone, this way or that way, as we discussed in the previous segment, consciously or unconsciously, the plane, the Euclidean plane in which the given circle lives, becomes the proverbial box. And again, this way or that way, we and the students who try to generate the corresponding proof shackle themselves to the confines of the Euclidean plane, not realizing that in mathematics in general, there's no codified rule which says that this specific problem can be solved if you stay only in the confines of the problem statement that is given. As problem solvers, we are free to choose any other mechanism that is legal and valid, of course. And the amazing thing about, I guess, the human mind in general is that our own human mind places us into that box on its own without anyone's help. And in some sense, the scope expansion problem solving approach is a constant reminder to let our mind and to let our mathematical imagination soar high in the sky above the ground, that is, the confines of the given problem. And in this specific situation, what do we do? In this specific situation, we unshackle ourselves from the burden, if you will, of the Euclidean plane and step into three space. And in the three space, we consider the mathematical object that is called an oblique circular cone. I designated this oblique circular cone with the letter K. And let's say that this cone has V as its vertex. One way to think about the oblique circular cones is as follows. First, we construct a right circular cone, which is actually known to be a solid of revolution, and I'll discuss how that can be done in a few segments later. And then we simply take the vertex of the right circular cone and push it a little to the side in such a way that the vertex of the new cone that becomes oblique circular cone does not project or does not fall precisely on the center of the circle that plays the role of the base of a right circular cone. But it is important to understand that in our setup, sigma 1 over here is still a circle. It is actually one of the crucial components, one of the crucial ingredients of our proof. So I'll write it down for you guys that sigma 1 is a circle. It is very important to keep this in mind, make it official, put it on the books, and understand that sigma 1 over here is a circle. It has O1 shown in yellow. I hope that you guys can see that this is a yellow in different color just to bring in some contrast. O1 is the center of the circle sigma 1, which plays the role of the base of our oblique circular cone named K with the vertex V. Here is the next crucial part. From our analytic geometry course, we may or may not remember that given such an oblique circular cone, there always exists another section of that cone with the plane that results not in a hyperbola, not in a parabola, not in an ellipse, but results precisely in the circle. And in this diagram, we show such second circle, if you will, also in blue. We call that circle sigma 2. Its center over here shown in different flavor of red. We refer to that center as O2. And again, because this is another crucial ingredient in our proof, I want to make sure that we're all understand that we're all on the same page, that sigma 2 is a circle. Those of our viewers who are at home with this fact, who feel comfortable with that fact, or remember from their analytic geometry course that this is the case, may skip the next segment. But for those of our viewers who are not that comfortable with that idea or who do not know that this is the fact, I will highlight the proof of that statement in the next segment. The material of this segment is optional because in this segment we will highlight a proof according to which, given any oblique circular cone shown over here, in such a cone, there always exists a second circle that is the result of the intersection of such an oblique circular cone with a specific plane. I will not go into all the possible specific details because this is the material that I will present in this segment actually belongs in a lecture, in a complete and full-blown lecture on analytic geometry. We are not doing analytic geometry in this episode. And in some sense, by going over the upcoming proof in a expedient fashion, we will also see that the art and the craft of constructing or putting proofs in mathematics together is an art and a craft of combining the units of existing mathematical knowledge that we somehow fish out from our own web of mathematical knowledge into a unit of new or not existent before mathematical knowledge. Now, in the lightning round from analytic geometry, again from the course in analytic geometry, we remember that cones, just like certain other mathematical or geometrical objects, come in two flavors: real cones and the so-called imaginary cones. In an appropriately chosen Cartesian coordinate system, a canonical equation of a real cone is shown over here. In words, it is x squared over a squared plus y squared over b squared minus z squared over c squared, and this whole sum is equal to 0 under the constraint that the reciprocal values shown over here of the real non-zero numbers a, b, and c, since we're dividing by these numbers. So the sum of 1 over a squared plus 1 over b squared plus 1 over c squared is equal to 1. Under the same constraint, the equation or a canonical equation in an appropriately chosen Cartesian coordinate system of an imaginary cone will be pretty much the same as the canonical equation of a real cone, with the exception that the sign in front of the z squared over c squared is plus instead of minus. So this equation shown over here under this constraint produces the so-called imaginary cone. Now, we will start with a real cone. We will work with a real cone, and such a cone, for example, we will take the equation for such a cone shown over here. Let me see, I forgot to put the a squared. A squared times x squared plus y squared minus z squared equals to 0 under the constraint that a is a strictly positive real number such that it is again strictly greater than 1. And then we'll consider the section of this here cone with the plane P, which we will take to be given to us in a parametric form. So the x coordinate of this plane will be given as a product of b times u. U is a new parameter. Y coordinate of this plane, every point in that plane will have the y coordinate that is equal to v. V is a new parameter. And every point in that plane for the z coordinate will have the expression 1 plus cu. Again, it may seem that this here equation is pulled out of the thin air. It's a magic rabbit pulled out of a hat. But again, this is not a fully blown lecture on analytic geometry. This is just a highlight. For now, we take it that's what it is. And the constraint on the numbers b and c is shown over here. B squared equals 2 over a squared plus 1, and c squared is the ratio of a squared minus 1 and a squared plus 1. What does that mean? It means that when we put these two guys together, boom, what do we get? The positive unity, exactly. B squared plus c squared is equal to 1. Now, how do we construct the byproduct of the intersection of two, let's say, surfaces in the old lingo or manifolds in the new lingo? Well, we put the one side of the equation of one geometric object as equal to the other. So in other words, over here, in order to determine the shape of the result of the intersection of the plane P, given over here in the parametric form, with the cone, with an oblique circular cone whose equation given over here, we do what? Precisely, we take our parametric representation of the plane. So we'll take this guy, slug him into x over here in the equation of the cone. We take our y, given the y coordinate given in the parametric form, and slug it into the equation of the cone over here, and we take z. So we take this material and we slug it into the z coordinate of the oblique circular cone, and if we can somehow massage it and produce an equation that we recognize, then we will be able to say, the intersection of this here plane with this here cone is blah. So what do we do? Well, now it's nothing more than middle school arithmetic. When we put b times u into this equation, what do we get? We get a squared plus b squared, times b squared times u squared plus y squared becomes v squared. This is this guy right here. And in the z squared, we basically square this term, 1 plus cu. And what do we get? -1, -2cu minus c squared times u squared. The square of this guy is equal to 0. And now what do we have? Now let us do this. Let us roll through this sum right here and group all the terms. Let me grab the green chalk and group all the terms that contain u squared. You see this guy, u squared. So this will be the term u squared, and this guy right here with the minus sign. So if we factor out u squared, what do we get? A squared times b squared. It's this gentleman right here, this guy. And what do we get from this term? Minus c squared. But however, this is in some sense the cleverness of constructing our coefficients b and c that way. What is this difference a squared b squared minus c squared? Well, here is the arithmetic again. It's straightforward, nothing beyond middle school. A squared b squared minus c squared would basically take b squared from here, c squared from here. A squared times b squared becomes 2a squared, and when we construct the difference, here we get minus becomes a plus, 2a squared minus a squared plus 1. Then it becomes what? A squared plus 1 over a squared plus 1. Bam! We have the positive unity, 1. So that means that this usual suspect over here, a squared times b squared minus c squared, is the positive unity, or 1 in plain English. And if we write down this observation over here, what do we get? 0 equals to v squared plus u squared, this is 1, minus 1 minus 2cu. And what do we have over here? Well, over here in this expression over here, we have a perfect square of u minus c lurking. All we have to do is, what do we have to do? We have to add c squared because we're missing the c squared and subtract it over here to fold it into this form. This is also, again, nothing beyond the middle school arithmetic. And once we do that, we fold this equation into this one. Now let's think about it in simple English, in simple terms. What do we have? A parameter, v squared, plus essentially another parameter squared, minus 1 plus c squared in that way. And what does that tell us? Well, it tells us that this is an equation of a circle in an appropriately chosen coordinate system whose radius is shown over here, 1 plus c squared. See? In other words, if we take this 0 away and carry this term over here, we will have precisely proverbial x squared plus y squared equals something squared. That something is this right here, square root of 1 plus c squared. Consequently, this expression over here represents precisely the circle. And now if we carefully again analyze, I'm not going to go into all the gory details, but if we carefully analyze this case, and then we'll have all the material presented, then we will have only two situations over here for the values of the coefficients b and c. That means that they can either be both in the same sign. So for example, it means that b and c both are greater than 0, or for example, b and c are both less than 0. In the second case, that means that b and c are of opposite signs. Opposite signs. In other words, for example, if b is greater than 0, then c is less than 0, and vice versa. If b is less than 0, then c is greater than 0. In these two cases over here, this is exactly what it means that two sections for an oblique circular cone will yield what? They will yield two different circles. These planes, in this case, when b and c are of either the same sign or opposite signs, these two planes will be distinct and they will not be parallel. Again, this is a claim that needs to be proved, but because this is not a lecture on analytic geometry, you guys can for now just take it, my statement, at its face value. If not, you can drill down, pick up any book on analytic geometry, find the corresponding area, and convince yourself that this is the case. But this is the case. These planes P will be distinct, they will not be parallel. Consequently, when these two planes intersect our oblique circular cone, then exactly two circles result. The circle sigma 1 that will play the role of the base of our oblique circular cone, and the circle sigma 2 over here shown with the center O2. And now that we understand that this is the case, we can move on to the proper proof of our statement in the problem S2M27. Now that we're all sufficiently convinced that given an arbitrary oblique circular cone, which has a circle as its base, in such a cone there always exists another section of that cone that is precisely a circle, we're actually almost done. And in its instantaneous sense, the technical essence of the upcoming proof will be a proof by contradiction. But by itself, that proof by contradiction cannot really hang in the greater beyond by itself. The only reason we can construct a proof by contradiction is because we had a clever and bright idea to step out of the 2 space into the 3 space and embed our problem into the 3 space situation of an oblique circular cone. That is, setting up a contradiction. Let's say that we claim that we have a finite description of a finite number of steps, following which, using nothing but the Euclidean straight edge, we can do this or that manipulations and locate the center of a given circle when that center is not given to us initially. Well, then the mathematicians will be very quick to observe the following. From this setup over here, it follows that the points V, O2, the center of the circle sigma 2, and O1, the center of the circle sigma 1, are not collinear. And what does that mean? That means that if we construct a straight line through the points V and O2, then the point O1 will never be on that straight line. Or, in other words, the straight line VO2 will never contain the point O1, and the point O1 will never belong to the straight line VO2. And conversely, if we construct a straight line, which I'm not showing over here, through the points V and O1, like so, if I do it carefully, you see, then the point O2, which is the center of the circle sigma 2, will not belong to that straight line, or in other words, the straight line through V and O1 will not contain the point O2, which will not belong to the straight line VO1. And what does that mean? What does that observation mean? Well, that observation means is the following. Let's say we somehow, as you claim, perform this finite number of steps of manipulating nothing but the straight edge in the plane sigma 2, and we somehow manipulate the straight edge and we manage to locate the center, the unknown center, the location of the unknown center O2. What does that mean? Well, if we place a point light source at the point V1 at the vertex of our oblique circular cone over here, what does that mean? If we shine that light, then in some sense every manipulation that we will perform in the plane sigma 2 will cast a certain shadow in the plane sigma 1. And that means that if manipulating our straight edge in a legal manner, we, for example, draw a straight line. Let me make sure that you guys understand this straight line. For example, we take our straight edge, we somehow manipulate it legally, we draw a straight line in the plane sigma 2, and this is a straight line that we drew over here. Then we move our point light source, wiggle it this way. What will happen? Well, this straight line will cast precisely this shadow in the plane sigma 2. In other words, under this sort of physics mathematical transformation of shining the light source on the plane sigma 2, the straight lines are taken into straight lines and points will be taken into points. And that precisely means that we have a contradiction, because if we somehow can locate the center of the circle sigma 2, that means that that straight line must pass also, its shadow must pass through the point O1. But this is not possible because the points V, O2, and O1 are not collinear, and that contradiction precisely invalidates our original claim that it is possible to come up with a finite description of a finite number of steps, following which it is possible to locate the position of the formerly unknown center of a given circle. And this is it. One more time, in order to drive that point home, the technical essence of the contradiction that we managed to set up in the previous segment amounted to the fact that the points V, O2, and O1 are not collinear in case of an oblique circular cone. And that means that if someone claims that they can come up with a finite description of a finite number of steps, following which, with nothing but the Euclidean straight edge alone, it is possible to locate the center of a circle, then that means that all these steps will be shadowed or traced, so to speak, in the plane sigma 1 if we are to place a point light source in the point V. And that means that if, according to that algorithm, the location of the point O2 can be recovered, that means that the shadow or the trace of that point must be highlighted precisely in the plane sigma 1 below, so to speak, over here. And that is precisely absurd or not possible because the points V, O2, and O1 are not collinear. And the question among students often comes up, how do we prove that in case of an oblique circular cone, the points V, O2, and O1 are not collinear? Here's one way to do it. Before we step up to an oblique circular cone, let us concentrate on a right circular cone shown over here. There are several ways to generate such a cone, and one way that perhaps requires the least amount of geometrical material is the following. Let's say we take an arbitrary straight line. On that straight line, we pick an arbitrary point, say right here, and then once we fix that point, we rotate our straight line about that point in space like so, and by doing so we will generate evidently two congruent right circular cones, one above, so to speak, the fixed point, one below. Let's say we throw the top cone out, and this is what we have over here, the cone thus generated. Another way that requires slightly more complicated arrangement, and this is what's frequently demonstrated or used in middle or high schools. It is said that, for example, if we take a right triangle such as VO1E over here and fix one side, for example, we fix the side VO1, then we rotate that triangle in space 360 degrees or 2 pi radians, then exactly we generate a solid of revolution known as a right circular cone. That is also the case, but admittedly, a right triangle is a much more complex structure than a straight line. Either way, let us say that we took such a right circular cone and cut it with the plane that is parallel to the plane of this board, or that is parallel to our monitors on which we watch this episode. Then the plane VDE will result. I hashed that plane in two different directions so that you guys can see it better. And the thing is that with a right circular cone, the fact is the triangle DVE will be precisely isosceles. In other words, in this triangle, the lengths of the line segments DV, as shown over here, will be the same as EV, or VD and VE. The line segments will have exactly the same length. But in such a right circular cone in which the vertex falls precisely onto the center of the circle, that is the base of that circle, of that cone, there exists actually uncountably infinitely many planes, each of which cuts that right circular cone perpendicular to the axis of symmetry VO1 and results in a circle, such as circle sigma 2 shown over here. In this case, it is important to understand that the smaller triangle, such as KVL, will also be isosceles, and it will be fully contained by the parent triangle DVE over here. And we know that in every isosceles triangle, the height shown over here, VO1, for example, is also a bisector, and it's also a median of the triangle when all these objects are constructed in a way that they emanate from the point V. But because the smaller triangle KVL is contained by the larger triangle DVE shown over here, that means that, well, these triangles will be similar. Again, it is not that difficult to show. The angles are the same. They share the same side. That means that the height of the triangle KVL, the height VO2, will also be its median and its bisector, and it will be contained by the height, the median, and the bisector of the larger parent triangle DVE, which is to say that the points VO2 and O1 will be precisely collinear. Now, what we do is we fix everything else, all the other material in this setup. We grab the point V, the vertex of our right circular cone, and we pull it to the side. And by doing so, we generate our oblique circular cone, where the vertex V as an orthogonal projection does not fall precisely onto the center of the base, which is a circle. Now, if we take our setup with the triangles KVL and DVE shown in the right circular cone case into the oblique circular cone case shown over here, the point K will be on that side, the point L will be here, the point D over here, the point E will be here. Then it is important to understand that the center O2 of the circle sigma 2 will sit, if we cut this oblique circular cone with the plane again that is parallel to the board or to our monitors, then the triangle shown over here, DVE, will result. And in this cross section of the oblique circular cone, what will happen? Well, in our right circular cone case, I wrote it down for you guys over here. The line segment KL is parallel to the line segment DE shown over here. But in the case when an oblique circular cone is cut with the plane like this, then the line segment KL will not be parallel to the base of our triangle DE any longer, because remember, in the earlier segments we proved that the planes that cut our oblique circular cone in a way that two circles result are not parallel. And from the fact that these planes are not parallel, it follows that in the corresponding cross section, the line segment KL will not be parallel to the line segment DE as shown over here. And in general case, the triangle DVE will not be isosceles as I reflected over here. So in other words, the length of the line segment VD will not be the same as the length of the line segment VE, but the center O2 of the circle sigma 2 will sit precisely on the bisector shown over here in green, the bisector VB of the triangle DVE. And that is precisely where the center O2 of the circle sigma 2 will be located. And in that case, again, it can be shown with enough torture of the material at hand that the triangle KVL will be precisely isosceles. And that fact is depicted over here. In other words, the distance VK will be the same as the distance VL. Consequently, in this case, now that we understand it, the point O, the center of the circle sigma 2, will sit precisely on the interior, on the bisector of the interior angle at the vertex V of the triangle DVE. But the point O1, this guy, when we cut it with the plane like so, and we construct this line, what will this line be that connects V and O? So because this is a circle, obviously O1E and O1D is the same. This is the radius of the circle sigma 2. That means that in our cross section, the point M or O1 will be precisely what? That will be precisely the foot or the base of the median of this triangle constructed from the vertex V. In other words, the distance DM, shown over here with the yellow squiggly, will be the same as the distance ME over here, but the point M and O1 is the same. I just wrote it down as a syntactic sugar device to show you guys that the point O1 precisely coincides with the base of the median of the side DE of the non-isosceles triangle DVE. So now, once that is understood, that the center O2 of the circle sigma 2 sits on the interior bisector of the angle at V, and the center O1 of the circle sigma 2 sits on the base of the median of this triangle. Now, for us, in order to show that the points V, O2, and O1 are not collinear, it is enough to go back to our case of plane geometry and recall pretty much a well-known and famous theorem, which says that in every non-isosceles triangle, such as the triangle DVE, the base of the interior bisector and the bisector itself always sits strictly in between the base of the height and the base of the median and the median itself. And that theorem, again, has a straightforward proof. And because that proof is correct and that theorem holds true, that precisely means that the points V, O2, and O1 are not collinear. And again, I cannot possibly prove all the intermediate theorems all the time, but because in this case there exists a very short proof, for those who really are interested in such a proof, I'll take 2 or 3 minutes to demonstrate it in public. In this short segment, for completeness, we will show a proof of the fact that in every non-degenerate Euclidean planar not isosceles triangle, the bisector of that triangle lies strictly between the median and the height when all these objects emanate from the same vertex of the said triangle. In other words, let us assume that ABC is a non-degenerate Euclidean planar triangle that is not isosceles, which means what? Which means that the length of the side AB is not the same as the length of the side BC, which is not the same as the length of the side CA. So all the lengths of all the sides are different. What do we do? Well, first, let's say we construct in green, we construct a height that emanates, for example, we'll concentrate on the point B, but we can do it with any other point. Construct the height of this triangle that emanates from the point B. This is this guy right here. We'll call this H. Then we cut this base AC in two. Let's say somewhere over here. This is the median, the midpoint of the base AC. In other words, we will say that the length AM is the same as the length MC. So far, so good. So this will be our median that emanates from the point B. And evidently, the bisector, which I will show in blue, let's say, roughly speaking, let's say this is our bisector of the interior angle at B. Let's call it S for bisector. Why not? So that means that this interior angle, the magnitude of this angle and the magnitude of this angle is the same. In other words, let's memorialize it. The magnitude of the angle ABS is the same as the magnitude of the angle CBS. We are to show that the points S, H, and M are locked into the following relationship. S is less than M and greater than H. This is what we are to show. Again, I'm committing a notational crime, but we understand what that means. With different arrangements, the points can be swapped. For example, the point S can be located to the others on the other side of M, but that doesn't change the essence. How do we generate a convincing proof? Well, the way we do it is as follows. We construct a unique circumcircle of this triangle. Let me see if I can do that remotely convincingly. So let's pretend that this is the circumcircle of the triangle ABC. What do we do then? Well, let us hijack the fact that the magnitudes of these angles are the same. Obviously, it doesn't look anything like it on my wonderful drawing over here, but if we extend the line BS, like here, this way, then this straight line will intersect our circle, sigma. Let's say this is our circle, sigma, so the straight line BS will intersect the circle, sigma, at the point, let's say P. This is our point P. And what can we say about that point? Well, the magnitude of the angle ABS and S and P are collinear, so the magnitude of the angle ABP must be the same as the magnitude of the angle CBP. And that means what? Let's write it down. So the magnitude of the angle ABP must be the same as the magnitude of the angle CBP. Would you agree? Yes, but that means what? Obviously, it doesn't look like on my Picasso drawing over here, but that means that the arc AP is the same, the length of the arc AP is the same as the length of the arc PC, and that means that the point P is the midpoint of the arc AC. In other words, this here distance, let me draw it, this distance and this distance must be the same. Let's memorialize it. So the length of PC is the same as the length of PA. I know it doesn't look like on the drawing, but if you carefully use, for example, GeoGebra or Desmos or any other graphical calculator, you will see that's precisely the case. So what does that mean? That means that the triangle APC, the triangle APC is isosceles. The triangle APC is isosceles, and what does that mean? That means that in such a triangle, again, it looks horribly out of proportion over here. Technically, this point must be here. In an isosceles triangle, the height, the bisector, and the median that emanates from the point P must be what? It must fall precisely on the point M. In other words, in theory, in general, PM is orthogonal to AC, and as I think it was Poincaré or maybe another person like him who said that geometry is an art of making correct statements based on incorrectly drawn figures. So there we go, incorrectly drawn figure, but the statement is the same. PM is perpendicular to AC. So, okay, let's maybe just fix this so it looks somewhat believable. So this way, this will be the point P. This is the arc. So in theory, so this angular bisector must come like this way. So PM over here, perpendicular to AC, the length PC and PA, the lengths are the same. And what does that mean? What do we have? The line segment PM is orthogonal or perpendicular to AC. And what about the height, our favorite height? It's also perpendicular to the line segment AC. So what do we have if we were to move this mass separately over here? What will we have? We will have the setup the following. This is B, this is H, this is H, this will run AC, this will be our point M, this will be our point M, somewhere here will be the point P, and if we carefully connect the points B and M, B and P, I'm sorry, here there will be our point S. This is perpendicular, this is perpendicular. What does it tell us? Exactly, it tells us that the line segment MH is none other than what? As it's none other than the orthogonal projection of the line segment BP onto, here we have A, here we have C, onto AC somehow. And that precisely means that the point B is located on one side of the line AC and the point P is located on the other side with respect to B of the line segment AC or straight line AC. And that means that when we project the line segment BP on the line segment AC, we get exactly the point H in M, and here there must sit precisely the point S, and that proves that in every not isosceles triangle, the bisector, the bisector of that triangle that emanates from a fixed side lies strictly between the height and the median of this triangle, each of which emanates from the same side. In this problem, we had quite a few moving parts, but once we understand how all these moving parts fit together, then if you guys time my performance in this episode in which I only talk about the essence and the meaty substantial part of the proof of the fact that it is impossible to locate the center of a circle with a straight edge alone, then you will see that all the material that I covered can be compressed in 2 minutes or 3 minutes tops. And why was that possible? Well, that was possible precisely because we decided, and that is the part of thinking like a mathematician and thinking out of the box, we decided to unshackle ourselves from the confines of the plane, and this is precisely what happens when people are given a problem on planar geometry. They somehow think that the only way to solve a plane geometric problem is by staying in the plane at all times. That is not the case, and that is the whole reason and the purpose of studying how the scope expansion problem solving approach works. It is in some sense there to remind us, to unshackle us from the box that the current problem is, let our mathematical imagination soar, and hopefully come up with a clever, elegant, and beautiful way to solve the problem at hand by stepping out or perhaps counterintuitively increasing the scope of the local material. And here is another point. I used this specific problem to demonstrate the following interesting fact. All the material that we manipulated in this exercise or in this problem was very straightforward and did not go in some sense beyond the proverbial middle school program. All we did is we worked with points, straight lines, and circles, and this is it. However, the creative part, the creativeness of the manipulation of this straightforward object is precisely the matter that makes the construction of this mathematical proof interesting. And I claim that this mysterious sauce, if you will, that glues together these straightforward to understand objects will be exactly the same when and if you will go on and you will be defending your PhD in mathematics, for example. But of course, in your work, you will not be manipulating points, straight lines, and circles. You will be manipulating much more difficult and much more abstract and complex notions, analytic continuations, field extensions, prime ideals, kernels of group isomorphisms, homomorphisms, and so on. But my claim is that the creative juices or the creative motive that surrounds the manipulation of this higher and more difficult material at hand will be one and the same. This is it for the discussion of the mathematical problem S2M27, and we will move to a new challenge next. Our next challenge will be a mathematical problem S2M28, and the objective of that problem is the following. Using precisely the scope expansion problem-solving approach, find a wholesale method to construct alternative expressions for the following finite sums. The sums of fixed positive integral powers of consecutive positive whole numbers. For example, this object can be represented as the sum in the sum notation for variable n, which runs between 1, 2, 3, 4, 5, 6, 7, and so on to a fixed number n. And each such number n, 1, 2, 3, 4, 5, is raised to a fixed positive integral power, such as 1, 2, 3, 4, or 5, and so on. For example, how would we construct the sum, the alternative expression for the sum of squares of consecutive whole numbers to the sum of cubes, sum of fourth powers, fifth powers, and so on. By now, all of our viewers should understand that in the big scope of things and in a good way, we do not really care about the answer that you can produce over here because we know that answer, but we do care a lot about your story that you can tell using the scope expansion problem solving approach, and how to construct such a wholesale method. Here you will face most likely the same problem that you faced in the discussion of the previous problem, because in general, the application of the scope expansion problem solving approach to a process of searching for a solution of a technical problem usually initially seems counterintuitive to many people. For example, in the several previous segments, when we solved the problem of how to prove that it is impossible to locate the center of a circle with nothing but the straight edge alone, we did something that usually, admittedly in many cases, does not lead to anywhere good. Stepping away from 2 space into 3 space is usually considered a much more elaborate and difficult endeavor, and that is really so. For example, rotations in the plane are commutative, but the moment we step from 2 space to 3 space, then the rotations of the sphere, for example, in general, are not commutative. And now, for example, we know that the mathematical objects, to which we refer as quaternions, then in general, they do not commute under multiplication, but the very fact that the quaternions do not commute under multiplication allow us to use them in order to explain or describe mathematically the rotations of the sphere in 3 space, which are not commutative. Likewise, in this problem, initially you may think that trying to increase the scope of the material at hand will not lead anywhere good, but that is not the case, and that is a challenge. There is a way to do it, and this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution based on the scope expansion problem-solving approach of the mathematical problem S2M28.